Hello everyone, welcome to Good Babe. Today we're diving into the mysterious and inspiring world of black holes, exploring their incredible life cycle from birth to its decay. Buckle up for a cosmic adventure. So let's start with the introduction to black holes. Black holes are fascinating celestial objects characterized by their incredibly strong gravitational fields, so intense that nothing, not even light, can escape from them. These mysterious entities challenge our understanding of fundamental laws of physics and have captivated the imagination of scientists and astronomers for decades. Black holes are shrouded in mystery primarily because their extreme gravitational forces defy our conventional understanding of the universe. The fact that they trap everything, even light, makes them invincible and difficult to study directly. Despite their elusive nature, the study of black holes provides a unique window into the profound effects of gravity on space and time. So before starting talking about black holes, first of all, we need to talk about the life cycle of a star. A star's life begins as a collection of gas and dust, which coalesces under gravity to form a protostar. The protostar undergoes nuclear fusion, converting hydrogen into helium, releasing energy in the process. For most of its life, a star balances the outward pressure from nuclear fusion with the gravitational force pulling inward. Let's now start talking about the black hole. Let's start at the beginning. Black holes are born from remains of massive stars. Massive. When a star much larger than our Sun exhausts its nuclear fuel, it undergoes a dramatic collapse. Gravity overwhelms the outward pressure from nuclear fusion, causing the star to implode. The gravitational collapse results in the formation of a singularity, a point of infinite density at the core. Surrounding the singularity is the event horizon, the boundary beyond which nothing, not even light, can escape. So, let's simplify a bit everything that I said. So to make this more easy to understand, stars are massive collection of mostly hydrogen atoms that collapses from enormous gas clouds under their own gravity. In their core, nuclear fusion crushes hydrogen atoms into helium, releasing a tremendous amount of energy. This energy is radiation, which pushes against gravity, maintaining a delicate balance between the two forces. Star is stable. But when this happens is in much bigger stars, which are like 4 times bigger as our Sun, the heat and pressure at the core allow to fuse heavier elements until they reach iron. Remember, the fusion process that creates iron doesn't produce any energy. Iron builds up at the center of the star until it reaches size in which delicate balance between the two forces, meaning radiation and gravity, is broken. The star implodes, moving about a quarter of the speed of light. Boom, 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 and the star dies into the supernova explosion. And then it produces a neutron star, which is so massive that if you would drop 1 tablespoon of neutron star on Earth, it will probably shatter Earth. Nothing will remain. It will destroy the planet. 1 tablespoon of neutron star. Or if the star is massive enough, it will produce a black hole. So, next topic is, let's cover up all the stages. Okay, in the final stages of a massive star's life, when nuclear fuels, displaced gravity overwhelms the outward pressure. The star undergoes a gravitational collapse, and if the mass is sufficient, it forms a singularity, a point of infinite density at the center of the black hole. By the way, black holes don't suck things up like a vacuum cleaner. Many people misunderstand this. If you would swap Sun with equally massive black hole, nothing much will change. Literally nothing. But we will probably freeze to death, of course. So, Black holes actually come with different sizes. There are stellar mass black holes which typically have masses up to 20 times that of our sun, formed from collapsing massive stars. Supermassive black holes found at the center of galaxies have masses of millions or billions of greater than our sun. Supermassive black holes. The exact formation mechanism of supermassive black holes is still topic of active research. There are also intermediate mass black holes fall between stellar mass and supermassive black holes in terms of mass, of course. Their existence is theorized, and there is ongoing research to detect and understand these enigmatic objects. The universe holds a range of black hole sizes, from the smallest stellar mass black holes to the colossal supermassive black holes found in every heart of a galaxy. Like, for example, in our galaxy Milky Way, the supermassive black hole is named the Sagittarius A. And these type of black holes are found in every galaxy, center of every galaxy. So, if you look at the black hole, this is really important part. When you look at the black hole, what you will really be seeing is the event horizon. Anything that crosses the event horizon needs to travel faster than the speed of light to escape. So it's impossible. The event horizon is a critical concept in black hole physics. Its boundaries surrounding black hole beyond which escape is impossible due to intense gravitational pull. Once an object, even light, crosses the event horizon, it is inevitably drawn into the black hole. The next topic that I want to cover up is the Hawking radiation. This guy was pretty important and played a huge role in discovering and exploring black holes, Stephen Hawking's groundbreaking concept of Hawking radiation revolutionized our understanding of black holes. According to Hawking, black holes are not completely black. They emit faint radiation due to the quantum effects near the event horizon. Hawking radiation arises from the quantum of fluctuations near the event horizon, where the virtual particle and antiparticle pairs spontaneously appear. If one particle falls into the black hole while the other escapes, the escaping particle constitutes Hawking radiation. Over immense time scales, black holes lose mass through Hawking radiation. This gradual process leads to a potential decay of black holes, challenging the perception that black holes are eternal and indestructible. So to understand this better, we have to look at empty space. So imagine that this is a black hole, and this is empty space. Empty space is not really empty, but it's also actually full with virtual particles popping into existence and annihilating each other again. When this happens right on the edge of the black hole, one particle will be drawn into the black hole and one particle will escape and become a real particle. So the black hole is losing energy. This happens extremely slowly at first, but it becomes faster as black hole becomes smaller. But this means that black holes can die. They are not eternal, as I said. But this process is incredibly long, like billions or trillions of years. Like when the last black hole evaporates away, nobody will be able to witness it. The universe will become non-inhabitable long before then. Yeah, unfortunate fact. So the next topic that I want to talk about is the information paradox. The information paradox arises from the conflict between the principles of quantum mechanics and general relativity. In the context of black hole physics, it questions the fate of the information that falls into the black hole and challenges our understanding of the conservation of information. To understand this better, black hole information paradox results from the combination of quantum mechanics and general relativity. As I said, the calculations show that physical information could permanently disappear into the black hole, allowing physical states to devolve into the same state. But this is controversial because quantum mechanics states the information can never be destroyed. So let's say that you burn two different letters written on paper. Okay, let's write one letter. Boom, boom, boom. There's something right on this letter, right? Okay. Now I decide to burn this. Don't I have? Oh, yeah, yes, I have a lighter. Okay, I wrote something down here. Boom. Boom. So there's something rolling on this paper. Boom. Let's make it burn. Boom, 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 boom. Okay. Kind of hot. So what happened? I have written something on this paper and I burnt it. Was information lost? Probably did, but is information completely lost? No. Why? So as I showed you, I have burnt a letter. Question is information lost? No, because the small difference between a smoke temperature and amount of ash would still retain information about this letter. Even though I have burnt my letter, something that I've written down on this paper, the smoke temperature and ash will still retain information. Okay, so information is not lost. But why did I say this? Because the problem with black holes is that they suck things up and over a very, very long time radiate what they swallowed back out in a form of Hawking radiation. But what if radiation doesn't contain information? Physicists say that information does indeed escape from a black hole by the radiation, and they have identified an invisible surface that lies inside the black hole's event horizon called the quantum extremal surface. This surface seems to encode the amount of information that has radiated away from the black hole evolving over the black hole's lifetime, exactly as expected if the information escapes. So something can actually escape a black hole, meaning information, because information could never be lost. But remember that this is just a paradox and we do not know exact answer to this particular question. So as I showed you, I have burnt a letter. Question is information lost? No, because the small difference between a smoke temperature and amount of ash would still retain information about this letter. Even though I have burnt my letter, something that I've written down on this paper, the smoke temperature and ash will still retain information. Okay, so information is not lost. But why did I say this? Because the problem with black holes is that they suck things up and over a very, very long time radiate what they swallowed back out in a form of Hawking radiation. But what if radiation doesn't contain information? Physicists say that information does indeed escape from a black hole by the radiation, and they have identified an invisible surface that lies inside the black hole's event horizon called the quantum extremal surface. This surface seems to encode the amount of information that has radiated away from the black hole evolving over the black hole's lifetime, exactly as expected if the information escapes. So something can actually escape a black hole, meaning information, because information could never be lost. But remember that this is just a paradox and we do not know exact answer to this particular question. The next topic that I want to talk about is the observational evidence and overall how was photo taken in 2019. As everyone knows, in 2019, if you were like 14 or 13 at least, you will probably seen the photo of a black hole, like a black spot in red around it. Some people were joking about this and thinking that it was the Snoop Dogg cigarette, or follow Snoop Dogg cigarette. No one thought it was a real. So I think that was taken in 2019. It was in April. I do not remember the exact date. And the name I think was Measure 87. I hope I'm not mistaken. M87 or something like that. So Photo was taken on some black hole. I think it was named M87, as I said. So, question is, how the heck did the Webb James Telescope, I think, took the picture of this black hole? As I said earlier, black holes are invincible, and that is true. And for you to see something, the light must reflect. Only reason why you are seeing me right now is because this is lighting towards me. Light comes towards me and it reflects, and you see me. Okay, and that's the only reason why you see me. Okay, so if you want to see a black hole, it must reflect light. But as I said, light can't escape from a black hole. So if this is a black hole and this is a light, but before that, we have to also discuss one certain topic. A light isn't just a wave, it's also a particle called a photon. And the photon doesn't contain any mass. Photon is massless, doesn't have any mass, but it has an energy. And gravity does apply to energy. Remember that. So when light starts its journey, let's say from here, and it goes right into the black hole will swallow this light. Okay? When it goes like this, it still swallows it, and best outcome will be like this. The curve happens because of gravitation, boom, 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 and it ended in here. Like it continues, but let's say it ended like in here. The journey started about here, right? Boom, and it came to here. So the curve happened, cross. So once I heard that when this curve happens, it creates a shadow, and scientists can take picture of this shadow, and that actually is what we were able to see in 2019. So the photo that you probably saw wasn't actually photo of a black hole, it was actually a photo of its shadow. And remember that that shadow is 4 times as big as the real black hole, so the size is inaccurate. Thank you for watching this video. Like and subscribe if you would like to see content like this. By the way, English is not my first language, so sorry for that. But still, I hope you enjoyed.